hydrochloric acid, and then what happened? Sorry? Yes. Nee, graad 9. Anyway. What did the container feels like? What did the container feel like? It was heating up. So an exothermic reaction, heats up. Why does it heat up? Because it releases more energy than what it takes in. So it gives off more energy than what it requires. Why does it need energy? To break bonds. Why does it release energy? When bonds form, it releases energy. Why? Because electrons are paired, orbitals are filled. So it becomes more stable, it becomes happy. Its potential energy goes down because it releases potential energy. Okay, so that is why when we look at the graph, you see the energy of the reagents are much higher than the energy of the products because it gives off more energy. The energy that it takes in is called the activation energy or the dissociation energy. What is activation energy again? The minimum energy required for a reaction to take place. Okay, and then it gives off energy. It's called the bonding energy. That there at the top is called the activated complex. It's the unstable transition state from the reagents to the products. It's where all the bonds have broken up, but they haven't formed new bonding pairs yet. All right. And then the heat of the reaction, or the net energy, in this case, will always be smaller than 0. It will always be a negative. Okay, so if we look at how we write this down, you can either have a negative or you can write it down as one of the products that form. Okay, and then we looked at this reaction, sodium hydroxide, that heats up, and we looked at magnesium oxide, where I burned the magnesium and it set alight. Ne? Right. Now, we have something called spontaneous and non-spontaneous. Spontaneous is it just happens by itself. It does not need, so spontaneous means it doesn't need any activation energy. You don't have to heat it up or stir it too much or anything like that. Because if it's spontaneous, it means it takes energy from its surroundings. Say again? It's independent of external energy, yes. Okay, so what we did, and the question that I asked Kali is, we took sodium hydroxide and I added it to water and it just dissolved. I didn't need to heat it up or anything like that, so it just happens. Okay, so it doesn't need any activation energy. So it means for a exothermic reaction that's spontaneous, the graph won't go up because it doesn't need activation energy. The graph will only go like this. It will go like this. It won't go up because it won't need it won't require activation energy. It just goes down. And then non-spontaneous reactions need activation energy, like heating it up. And this is what happened with magnesium. I had to put a flame there. I had to heat it up to get the process going. And when the process started, it just happens by itself. Okay, so here you'll have a triangle under the arrow every time. Sia, what does the triangle represent? It stands for delta, yes, but what does delta represent in this case? No, not in this. When it's an arrow, a triangle underneath the arrow, it stands for something else. Yes? It was heated up. Heated. So it means there's a flame. Okay. Then we get something like an endothermic reaction. An endothermic reaction. Okay, so that exothermic, like exit, it gives off more energy. Endothermic, it takes in energy. In, it requires energy. So it's a reaction that absorbs energy. Rory, give me another example of something, anything that absorbs something. A pot absorbs what? Okay, no, don't make it fancy. Don't make scientific. Like in your everyday life, you use a few things that absorbs stuff. Absorbs what? Yeah. What does your phone absorb? Don't listen to Khali. You're making it too complicated. Your skin. When you put on cream, what happens to the cream?
Disappears.
Why?
Into the skin.
Into your skin. Your skin absorbs the moisture, especially when it's so dry and cold like now. When you have a sponge, when you clean your pot or your pan, or a sponge when you shower or your bath, it absorbs the liquid, the moisture. Yes? Okay, so your skin also absorbs the UV rays from the sun. Okay, a black t-shirt, like Clooney says, will absorb heat and it will keep you warmer for longer if there's heat present. So there's lots of things that absorbs, like your hair or your beanie or whatever absorbs heat particles and it keeps it there. Yes? Right? Absorbs. Okay. So an endothermic reaction is a reaction that absorbs energy. It takes more energy in than what it releases. Okay. So there you can see the heat of the reaction is going to be greater than 0. Because it's going to take in more energy than what it releases. Okay, so here I have another hypothetical reaction. Hope, what does the word hypothetical mean? It's not in there. I just said, this is another hypothetical reaction. Okay, hypothetical reaction. Right, so here it is. On our y-axis, we have potential energy in kilojoules per mole. And on our x-axis, we have the reaction coordinate. That can be time or just how the reaction takes place or something like that. Okay, so here you can see the reagents. We start with energy of the reagents. And then it takes in energy to break the bonds. That energy that it takes in is called the activation energy, or it's called the dissociation energy, because it dissociates, it takes apart the bonds, it dissociates, it breaks up the atoms. Then there at the top we have our activated complex. It is the unstable transition state. Unstable transition state. So that unstable, thus they have a very high energy. High energy. Do you have it? Not yet. Say again? Okay, read it out loud for everyone. Hypothetical. Now, what is the first word in bold? Loud. Everyone must hear. Theoretical. And then? Yo, oh. You can speak so loud outside of the class, but in there you will break. It says, theoretical, academic, assumed, conjectural, imaginary, putative, speculative, supposed. So, theoretical is what I want you to look at, and also imaginary. Okay, so when I say it's a hypothetical reaction, it's an imaginary reaction. It's something that we say, let's assume, let's pretend, let's play pretend. Okay, stop. Fill out yourself with verder. As ek hom weer sien, vat ek hom. Alright, so this reaction that we have here is just a pretend reaction. Okay, let's play pretend, let's assume, imaginary reaction. Alright, so here at the top we have our activated complex, that's the unstable transition state. You can see it has high energy, high potential energy, because all the bonds are broken, they are moving around, they're trying to find their partner again. Then when it gives off energy, when it releases energy there, that energy is called the bonding energy. It releases energy, the bonding energy. But you can see it doesn't release as much energy as what it takes in. Okay, it releases less. It takes in more. It absorbs energy. So you can see the energy of the products are much higher than the energy of the reagents. Okay, then this here that we have is called the heat of the reaction. It's the difference between the energy of the products and the reagents, or the reagents and the products. This is actually the wrong way around. This is must be E2 minus E1. Okay, now let's play pretend. Let's put in hypothetical values. Let's say this is 50 and this is 1,000 and this is 2,000. Yes.
So in the exothermic reactions, is it fine the E1 minus E2?
Yes. Okay. Let us begin. For the reaction, what is the value of the activation energy? What is the value of the activation energy? Tony, your question will be, what is the value of the bonding energy? Courtney, your question will be, what is the heat of the reaction? Value of the heat of the reaction. Yes, Mr. Bilay?
Isn't it going to be 1,950?
1,000? Yes, because from here to there is 2,000 minus 50 gives you 1,950. Okay? Here's Flonnie, what is the bonding energy? How did you get to that? 2,000 minus 1,000. And what is the heat of the reaction? How did you get to that? 1,000 minus 50 is 950. Okay, you weren't here. Nekalo. What is the heat? No. What is the activation energy for the reverse reaction? What is the activation energy for the reverse reaction? No, for the reverse, this is the forward reaction. This is the reverse reaction. Activation energy is from the start to your highest point. Yes? So from your start to your highest point, so where did we start? 1,000. Highest point was 2,000, so the activation energy will be 1,000. Okay, so what is the heat of the reaction for the reverse reaction? No and yes. No, the value 950 is correct, but the symbol is wrong. Because it is heat of the reaction, it is the products minus the reagents. So it's 50 minus 1,000 gives you minus 950. Chop. Can you see if the forward reaction is endothermic, then the reverse reaction is exothermic? Yes? Okay. So I've told you this at the beginning of this lesson, but I'm going to say this again. I can either give you a graph or I can ask you to draw a graph. You must know this shape there is always endothermic. And you must know the reverse shape, this is always exothermic. Okay? Then, we went here. Ona, what does the dotted line represent? It is when you add a catalyst. And a catalyst has two functions. Function number one is it lets the reaction takes place faster. It is completed faster. That's why you can see there, it is the dotted line completes the reaction faster. And number two, it lowers the activation energy required. So that is why that line is smaller, is lower. Okay, then how do we write it down? With exothermic reactions, you said comma, and then the heat of the reaction is negative. With endothermic reactions, you're going to say comma, and the heat of the reaction is positive. Or, since it absorbs energy, since it needs more energy than what it gives off, the energy can be one of the reagents, Okay, and then there's few examples of spontaneous and non-spontaneous. Spontaneous, it does not need activation energy, as you do not need to heat it up, but what happens is it absorbs heat from its surroundings. Like, the one that you'll know best probably, is when you have a salt that you have to dissolve in water. When you take salt, normal table salt, and you put it in cold water, what will happen? Will it dissolve? It somewhat dissolve, but you'll actually see the water going down. And what you will also see, and if I have time, I'll show it to you now in a video, sometimes the water actually starts to freeze. Because what happens is the salt, to split up the salt takes the heat from the water. The tiny bit of heat that is still left inside the water molecules, it takes it and it makes the water colder, and then the water freezes up. Okay? So that's an example of spontaneous. It happens by itself. You don't have to heat it up or anything like that. And then the other one is a non-spontaneous one where you need to heat it continuously. You need to keep it going. Like, for example, copper sulfate, hydrated copper sulfate. Here I have this. Hydrated copper sulfate. Okay? If I take this and I heat it up, then this water here will evaporate. It will go away. So, you'll actually hear it goes. So the water evaporates, and then you're left over with copper sulfate, and it's a white powder. But as soon as I turn off the flame, the reaction stops. And then when you put the flame there again, it will start to evaporate. You put off the flame, the reaction stops. It's like cooking food. Yes? Okay. There's something else that I wanted to show you. Okay. What do I want to show you first? Let's see if I can show you that YouTube video. While I'm looking for that, next week is Science Week. On Monday, first break, I'll have experiments here in class that I'm going to do. Tuesday, there'll be a Sudoku competition in my class. Everything will happen in my class at first break. Okay, so first break, you can come if you want to take part in the competition. I'm going to hand out Sudoku papers, and then when you're the first one to complete it correctly, you get a reward. Wednesday, there will be a competition, so you can send in Monday, Tuesday, Wednesday. You can send in a joke like this, and then the joke that I consider to be the funniest joke will get 50 Rand. And then Thursday, there will be a Kahoot science competition. You know Kahoot? Okay, but you need to bring your own cell phone, you need to have your own data. And then we'll play a Kahoot game, and then the winner there wins a prize. And then Friday, in class, hopefully, we will make sugar bombs. Just a bomb, if there's time in class. Okay, so that's next week, so you can start to think so long. Yes?
You said the salt, when you put it in water, going to freeze it up then. So the fridge, like normal fridge, how does it like inside? Does it salt?
Let me just see. I'm seeing what I'm wanting to see. Wait, sorry.
7 out of 10 yogurt lovers prefer Camelot.
Here's how you can instantly freeze a bottle of water just by hitting it on a table like this. Alright, so first you're going to want to grab a transparent bottle like this, preferably one that previously had blackberry lemon. Then take off any wrappings that are around the edges. You should now have a naked bottle. Then fill the bottle with cold water. Then stick it in the freezer, and we're going to leave it here for a couple hours. Now, the reason why this works is because we're super cooling the water to the lowest freezing point. But the reason why it doesn't freeze, it's harder for the water to transition from a molecular level from a liquid to a solid state. So hitting it on the table jumpstarts this process by lighting a few molecules. And this process is called nucleation. Okay, it's been in the freezer for a few hours now. And exactly how long you need to leave it in there really depends on your freezing. Now, I need to be super careful to not bump it, so I don't start the nucleation process too early. Now, you can see that it's clearly still a liquid. But watch when I hit it on the table, it'll start a chain reaction and immediately start freezing from the top down. It happens really fast and looks super cool.
Can you
Now,
see?
the bottle is fast and looks really cool. If you enjoyed the video, make sure to like and subscribe, and I'll see you in the next one.
So what happens is he puts it in a bottle with that had blackberry hydration something in it previously, and that has salts in it, so that does help the process along. Okay, anyway, it's quick.
And the force applied.
And the force helps the molecules to align. All right, let's look at this example here. It says methane gas. So it's a reaction that we had on page 1. Methane gas reacts with chlorine gas to form methyl chloride and hydrogen chloride according to the structure formula and incomplete energy profile, blah, 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 blah. Okay, so there you can see, I told you we started the reaction, but it's not complete. Okay. Now let's calculate the dissociation energy for this reaction to occur. Now we've done that already on page 1. We said the dissociation energy for this reaction to take place is there. Are you with me? Okay. So I'm just going to say we calculated that on page 1, and the dissociation energy was what again? 657 kilojoules per mole. 657 kilojoules per mole. Then calculate the bonding energy for this reaction. We also did that on page 1. The bonding energy was 770 kilojoules per mole. Okay. Then it says, determine whether the heat of the reaction, the enthalpy, the delta H, has a negative or positive value. So to calculate that, sorry, this was negative, because it releases energy. That negative means that it releases energy. This positive means it absorbs energy. Okay, so if it's negative or positive, so if we look at the change in energy, it's 657 minus 770, and that gives you minus, what was it, 113. 113 kilojoules per mole. So it has a negative value. So what does a negative mean? It means it releases energy into the surroundings more than what it takes. So, Tsepo, does that mean it is an exo or an endothermic reaction? If it is negative. It is an exothermic reaction because it releases more, the word more is important, more energy than what it requires. Lesedi, what does the word require mean? It needs. Okay, you need a ruler. Now it says, assume that the energy of the reactants is initially 0. Okay, so hardly ever be 0, but let's assume it will be 0. Redraw and complete the graph. Include relevant energy values on the axis as well as the enthalpy. Okay, so there we have our graph. On the y-axis we have our potential energy in kilojoules per mole. And on our x-axis we have time. Binne? Waar gaan jy?
Die laaste periode terug.
Regtig, vir wetenskap.
Ja, en die extra klas op van naskool.
Ja, asseblief.
So ek kom terug.
Dankie, sterkte. Okay, where are we with our questions? Khali, back to you. Please show me with your hands, what does this shape for an exothermic reaction look like? The shape for an exothermic reaction. Like, how does it go? So does it end lower or higher? Ends lower. Okay, so they say the reactance is initially at 0, so we start there at 0, and then it will go up, and then it ends lower. Okay, so you start with your shape. Now this does not have to be drawn to scale. Okay, your homework. Your homework is on page 6, the whole of page 6. It looks a lot, but it's not. It's really not. It will take you 5 minutes. The whole of page 6.